the position from here to here is 9.5 divided by 2. Okay. So that's how we determine is the global centroid multiplied by the individual centroid. So 80 times by 9.5 power 3 divided by 12 is 5.715. Wait, 9.5 power 3 times by 80 divided by 12. 5.716 times 10 to the power 3 plus, so 60 plus by 9.5 minus by 9.5 divided by 2, squared the whole thing, times by 9.5 times by 80. So it's equal to 3.186 times 10 to the power 6. So this will be equal to 5.716 power 3 plus by 3.186 power 6. So it's equal to 3.192 times 10 to the power 6 millimeter to the power 4. Okay. Next, we do IZZ for the web. So the IZZ for the web, again, the formula is the same with depth cube over 12 plus by capital Y bar minus small y bar squared. But for this case, right, for the web, this whole term over here is equal to 0 because the global centroid and the web centroid, which I draw in blue, are overlapping the same position. Okay? So that's why the second term is equal to 0. When that's the case, the width is equal to 9.5. The depth is equal to 120 cubed over 12. Okay? So 9.5. So this is equal to 1.368 times 10 to the power 6 millimeter 4. Let me do it again. 9.5 times 120 power 3 divided by 12. Yep. So finally, we can compute IZZ will be equal to twice 3.192 times 10 to the power 6 plus by 1.368 times 10 to the power 6. This will be equal to 3.192 power 6 times 2 plus by 1.368 power 6. It's equal to 7.752 times 10 to the power 6 millimeter 4 or 7.752 times 10 to the power 6 meter 4. Okay. So we know that IYY will be equal to what? IYY we calculated earlier is equal to 8.819.24. Okay, 819 times 10 to the power minus 6 meter 4. And we just computed IZZ will be equal to 7.752 times 10 to the power minus 6 meter 4. Minus 9. Sorry, the first one is minus 9. Can you change to minus 9, please? Okay. So in this context, buckling will occur in the XZ plane, and this is because IYY is less than what? IZZ. So basically, IYY has If the value is lower, when the value is lower, it means less resistance to what? Bending, or in this context, buckling. Right? It makes sense, yes or no? Okay. Just to quickly recall. If you look at the front, view from the front, right? If we need to bend the structure in this way of loading, relative to this way of loading, yes or no? The reason because the depth. Remember, the resistance to bending is the depth Q. Right? You have so much depth, you have higher resistance to bending. Is it clear now? This is your lead, this is your depth. You have to be very clear about it because later on, you have to make a decision to determine which axis that buckling is going to occur. Okay? This is just half of the difficulty over here. So when this is the case, we realize that buckling will occur in the exact plane. Okay, and so exact plane. Okay, so if you look at this diagram over here, right, we draw exact plane. So buckling now will occur looking like this. Okay, that is our exact plane. So from here, we are going to calculate the critical load at the exact plane. You just call it exact. Okay. So this will be equal to pi squared E multiplied by IYY over L squared. Now I'm going to also do the other side. I also want to calculate the critical load, okay, on the other plane, which is your XY plane. Okay. And now this is equal to pi squared E, just to let you have a look what is going on. Divided by L squared. Okay. So for this case, you have pi squared. Young's modulus is 200 times 10 to the power 9. IYY is 819.24 times 10 to the power 9. The length over here is your length is equal to 6 squared. Okay. So from here, we can calculate pi squared is equal to 44.920 times 10 to the power 3 Newton. Okay. If we were to calculate using IZZ, okay, so this is still the same. However, your IZZ is at a much higher amplitude. And then your L squared is 6 squared. Okay. So shift by squared times by 200 power 9 times by 7.752 power minus 6 divided by 6 divided by 6. So it can withstand 425.051 times 10 to the power 3 Newton. 10 times. Okay. 10 times larger, about 10 times larger than in the exact plane. So therefore, the factor of safety will be equal to 44.9 0.92 times 10 to the power 3 divide by, so let me write out the formula first, okay? So it's P critical divided by P, okay? So P critical is 44.920 times 10 to the power 3 divided by P, which is equal to 16 times 10 to the power 3. Now this 16 is given. Okay. So 44.92 power 3 divided by 16 power 3 is equal to 2.81. Okay, safety of factor. Okay. Then you have to do another check. Okay, you have to check to ensure that the stress critical is, it has to be lower than the yield. Now this is extra, okay? We're not given a yield, but you have to check. Okay. So stress critical is equal to P critical divided by cross-sectional area. Okay. So cross-sectional area does not matter whether is it the X or the Y, yes or no. Okay. So this will be equal. So let's look at the area. So the area is 9.5 twice of 9.5 multiplied by 80 plus by 120 multiplied by 9.5. Okay, so this is for the flange. Over here, this is for the web. Okay, so 2 times by 9.5 times by 80 plus by 120 times by 9.5 is equal to 2.66 times 10 to the power 3 millimeters squared. Let me do it again. 2.66 times 10 to the power 3. So in meters is equal to what? 2.66 times 10 to the power minus 3 meter squared. Why that's the case, right? Is because from meter to millimeter, you have to times 10 to the power minus 3. So it's 10 to the power minus 6. Minus 6 plus 3 is minus 3. So when that's the case, you have your stress critical is equal to P critical, which is equal to 44.920 times by 10 to the power 3 divided by 2.66 times 10 to the power minus 3. Okay, so 44.92. So it's equal to 16.887 times 10 to the power 6 Pascal. Okay, and let's say if we assume or given that stress yield is equal to 120 megapascal. Okay, so given, so we know that this is less than stress what? Yield. Okay, then you have to write down the structure is what? Is safe. If it's greater than 120 megapascal, no doubt no doubt it will not. If let's say this is higher than 120 megapascal, the structure is not safe. Are we clear? Okay, so you have to check. So two things that you have to check. What did we learn today? Okay, most important that you have learned today is how to determine what is your IYY and how to determine what is your IZZ. Okay, what is the width and what is the depth. Then from here, more important, once you have calculated your what? Your critical load, your factor of safety is your critical load divided by P. And which second moment of area to choose? The one to choose is the what? The lower one. Are we clear? And then again, we have again to check to ensure that the critical stress is less than the what? The U stress. Are we clear? Okay. Tomorrow, we'll do something different. We'll look at different boundary condition under extended Euler's condition. Okay. I'll see you guys tomorrow. Thank you for your time.